Hi, welcome to part two of the Introduction to Deep Learning with Bifrost series. In this part, we're going to use Bifrost to build a procedural data generator to generate a data set that we'll use for training our neural network. As a reminder, we want to create an IK solver for this 3-axis mechanical rig, and we're going to use forward kinematics to produce our training data. To generate a training sample, we're going to generate 3 random angles for theta 1, theta 2, and theta 3, run those through our forward kinematic solver, and then measure the resultant end effector location. In the Bifrost browser, we have a new sample graph that does exactly this. In this part of the tutorial, I'm going to walk through step by step how to build this graph from scratch. And this graph doesn't actually use any compound specific to machine learning, but it does use a new compound called write NumPy that the Bifrost team added with the machine learning compounds that will write the data we generate as NumPy arrays in .npy files. If you're not familiar with NumPy, it's a super popular Python library for working with arrays, and it's used really heavily in machine learning. I actually think this is a super valuable compound even outside of machine learning. Makes it really easy to export all sorts of array data from the graph so you can use it in different parts of your pipeline. In any case, this browser sample doesn't include geometry, so we've included some geometry separately that you can download. Slightly different than the geometry I have here, but the kinematic setup is the same. And how this is set up from the start is I have the meshes here in our geo group, and then I have 2 controllers. I have a controller that we're going to use for the root so that we can parent to things. I have a controller for the IK handle, and then I have a bunch of locators. So what these locators are going to do is tell Bifrost where we want our pivot points to be on this rig. So I've already set those up. So I have one at the base here. I have one where axis 1 is going to rotate, one where axis 2 is going to rotate, one where axis 3 is going to rotate, and then where we want the end, what we want to consider the end of this robot arm, where we want our IK target to be. And then the last thing I'll note is that I have locators that are parented to these controllers, and that's just so that when we drop them into Bifrost, Bifrost can read the world matrix. So if I just have this root controller and try to drop that in, that's not going to work, but we actually want the matrix of that. So as long as I move this around, that root matrix will update properly. Okay, so open up Bifrost, create a new graph here, and the first thing we're going to do is create our forward kinematic setup. So again, one of my main conceits here is it's actually quite simple to set up the forward kinematics of this compared to actually going through the process of creating a normal IK solver. Give myself a little more room here. So in a forward kinematics setup, on a serial chain like this, it's pretty straightforward. So we're basically just going to transfer any transform that's made on a specific joint down the chain. So if we rotate this joint here, we're going to want to rotate everything that's below it up. Similarly, if we rotate the next joint, we want to similarly transform the joints, the children of that. So to do that, we can use one of our new rigging nodes, and we can actually do this in an iterate loop so that we can just transfer each of those operations down the chain. And we're going to use iterates because the order of operations matter, so this has to be sort of cascade down the joint hierarchy. So I'm going to delete my max iterations, open this up, and then drop down a compute transform node. This is a new node, I believe, with the new rigging nodes. And then we want to send our pivot and operator matrix nodes to the inputs, make sure both of them are set as iteration targets. So this is going to iterate over all inputs, pivot matrices, and then all of the operators for each of their matrices. So the pivots are designed to be static, so you set that up once, and then any operation you want to do on top of that, so if you want to rotate about a certain axis, that's all stored in operator matrices. So we're going to have one pivot matrix for each joint, and then one operator matrix we're going to be able to control. And then we want the parent transform, which is going to be, we're going to set up to be this, this root controller out here. And then as this iterates, it's going to take pivot of joint 1, sorry, pivot of joint 0, operator matrix of joint 0, apply the transform, and then we want that transform to become the parent transform of joint 1, and so on. So what we're going to do is set this output transform here to a feedback port and set that to parent transform. So this will update the current transform of the hierarchy as it cascades down the chain. We also want to keep track of where the transform of each joint is as we go. So we want to duplicate this here, but set this one to an iteration target. So if we pop up one level here, you'll see that's going to be an array of transforms. So one transform for each joint. And then we have our feedback port. And this right here is going to be our FK solver. So we want to start dropping in our pivots here. So select in order, the order matters here. Select locator 0 through 4, middle mouse drag those in, and now we have an array of our pivots. We can pass in there. And then next, let's set up our parent. We're going to bring in our root locator, which is going to be our parent matrix. We're going to use that same compute transform node for the roots, and we're going to make that root matrix the operator, and then the pivot matrix here will just be identity, and then we're going to pass that in to initialize the parent. All right, so with that done, this actually isn't going to work yet because all of our operator matrices here are 0, so this node isn't, it's going to zero everything out. Let me reset this. Let me reset this. And next, what we want to do is construct our operator matrices. And this is where we're actually going to have our forward kinematic controls that our model is going to write to, that we'll be able to move around just like in Maya. You can rotate on an axis here. We'll have a little control. In Bifrost, you'll be able to rotate, and the axis will rotate. So let's create a compound here. We'll call this FK controls. Let's head inside. We're going to use a build array node, and we want to create 5 input values. So we're actually only going to use 3 of these because only 3 of our joints here are going to be rotating, but we need to build 5 operator matrices, so this will just help us keep the number of everything consistent. All right, and then we're going to intercept basically the middle 3, and we're going to want those to be our FK controls for axis 1, 2, and 3. So pass this out. Rename these theta 1, theta 2, theta 3. And then what we want to happen is we want a single float value to represent the rotation of a joint on a single axis. So these are rigid joints here. They only rotate about one axis. And then from that rotation, we actually want to construct the operator matrix that we can apply to the transforms. So we're going to use a for each node to do that by connecting all of our individual rotations here. And then we're going to build a second array here that's going to be of float 3s. So these are going to be the axis in which we want each joint to rotate. So I'm going to create a value node, set this to a vector 3, and then do the same thing. So we're going to do this 5 times. And then again, the middle 3 here are going to be our axes of rotation for axis 1, 2, and 3. 2, 3, and the others we can just set to 0 because we don't want any rotation on those. So for axis 1, that's this one right here. Again, we're going to rotate that about the x-axis. So we're just going to put a vector. We're going to set x to 1, the others to 0. Axis 2, we want to rotate about the z-axis. So we're going to set the z-axis to 1 here. And from those components, we are going to, for each input, rotate around that vector that many degrees. So in our for each node, sorry, we gotta pop back up, make sure we connect our axes, clean this up, rotation, and axis. Set our axis also to an iteration target. We're gonna work in degrees, just find it easier for FK controls, more human readable, but rotations like to be in radians, so we're gonna convert all of our rotations to radians here. And then use a node called axis angle to quaternion, where we're gonna do exactly that. We're gonna use our axis, rotate it about an angle, and we'll get a quaternion, and then we're gonna use the node SRT to matrix, which you can input a quaternion and it will give you the appropriate matrix for that transformation. Pass that out. Now we have our transform here, and we're going to pass that out. All right, so that's going to be an array of our operators based on the inputs we have here. So if we connect that, that should be good to go. And I noticed that we actually haven't brought in our meshes yet to visualize. So these are still just in Maya. Maya has no idea what's going on over here yet. So what we need to do is bring these in to Bifrost so that we can visualize them on the Bifrost side. So to do that, let's make a little rig scope. We're going to go back to our main graph here, where now we have our FK controls, we have the FK solve, and then we have our transforms. So what we want to do is take those transforms and then apply them to a skeleton in Bifrost. So we can start with using the skeleton scope. I'm actually going to hide the geometry for a second here. And then construct skeleton. So right here we have a transform type. This is part of the new rigging nodes that help you do a lot of easy operations on joint transforms. So the first thing we can do is use the access transform matrices. And if we plug in this array of transforms, this will actually auto loop. So we'll be able to get an array of all of these values with an auto loop. And then from the world matrix, we can plug that into joint pivot matrix for the skeleton. So joint parent index is just a list of integers that describe the hierarchy of the rig. So in our case, everything is parented to in a sort of serial manner. So we can actually just input a sequence array here, and we're going to do that by dropping down an array size node and then doing a sequence array of that size. And we want to start at -1. Make sure this is an int. Start at -1. And what that does is it basically indicates the first item in this list as the root. And then everything is parented on the way down. And step 1, connect the skeleton and display. So now we have our skeleton. We can change maybe the joint color here. And then let's test our FK controls. So first let's check our root. That seems to be working. And then theta 1, again, should rotate along the y-axis, sorry, the x-axis. Theta 2 on its z-axis. There we go. And theta 3 also on its z-axis. There we go. So I'll also note that if we had a different, slightly different kinematic setup where the joints had different lengths, we can move these locators, close Bifrost real quick. If we just move these locators, this will update procedurally. So it's a really nice part of the Bifrost rigging pack here. It'll be easier if I zero those out. Yeah, so we can move these kind of all over the place, and then those controls will still work just fine. Undo all of that. Make sure we're in the right spot here. Set these back to 0. Okay. So now we know the rig works. Next we want to get our meshes in. So let's take, again, select these in order, take our meshes, middle mouse drag into the graph. And then we're going to do another for each node. Instead of using the world matrix here, we're going to leverage this axis transform matrices, which has done a nice some nice computations for us. One of them is move world matrix. So what this is it's a matrix that represents how far something has moved in relation to its default state. So if we look at these meshes here, when we transform this around joint 1, for instance, we want to move joint 2 by a relative value from the start position. That's kind of the same amount as that original transform. So move world matrix, plug that in, and then plug in our geometry. And then we need to transform each point on that, essentially transform every point on each mesh by its corresponding move world matrix. To do that, we'll use a get point position. Also make sure this is an iteration target here. We'll get point position, transform as position. So it's going to take a position, transform it by a transformation matrix, and then we want to set the new point position back on the mesh to the transformed position and then output. And then we'll drop in a terminal here, plug that in, hide the Maya geometry, and now you'll see fresh Bifrost geometry here. So if I hide the Bifrost graph, you'll see that mesh toggle. And let's once again check that our FK controls work on our new mesh. There we go. All right, theta 1. Let's do this manually here. 10, 20, 30. Okay, so now forward kinematics works. So I'm going to do a little bit of cleanup and combine all these things into a rig scope. First thing I'm going to do is I'm just going to move the out geometry terminal port to proxy. So that way the skeleton is on a diagnostic terminal and then our mesh is on a proxy terminal. Then select all these, group that. You'll notice this errors. That's because this is expecting, because of the auto loop, Bifrost is sort of expecting a single transform, but we actually want to pass in the array of transforms. So I'm going to set port type. It's already set to transform. I'm just going to make that an array, pass that in. So now we have our geometry on the proxy terminal, and we have our skeleton, if we need it, on the diagnostic terminal. And I'm going to call this rig scope, and then we'll be able to reuse that in the future. Okay, so that is our forward kinematics setup. Next, we're going to make a data generator so that we can procedurally toss this rig around and then get the inputs and outputs that we want for our neural network. One more bit of cleanup here, which is to create a compound out of this. And I'm going to call this XZZFK. So just to note, if we had a different rig setup here, and we wanted maybe the first joint moved around the y-axis and the second one the x-axis, we can create another one of these and just make sure that the axes here match. Maybe we want a prismatic joint. We want something that translates linearly. You can set up a new FK controls for that. So this one's going to be specific for this 3-axis rig that rotate around these particular axes. And then we're going to do a bit of housekeeping on this guy, just rename a couple things. And then I'll go in and make sure that we have axis 1, or theta 1, 2, and 3 as inputs. So now we'll lay this out. This is nice and clean here. We have our controls right there at the top of the compound. And we can copy and paste this into some other compounds we're going to make for data generation. So for data generation, what we want to do is create a compound that randomizes the joint values. So we want 3 values per sample, 1 for each joint. And then we want to send that through this node here and then get the resulting transforms. In fact, I'm going to output these transforms just to be clean. And then from that, we'll be able to assemble our inputs and outputs for the training process any way we see fit. So let's get started with our generator, create a new compound here. Call this XZZR for right. This is the right side. You can do a separate one for the left, or reuse. I'm sure we can figure out a way to reuse the same generator. Call this V1. And this we're going to want to pass in basically everything that we have on here we'll want inside here. And starting with our pivots, which are going to be this array, we need our root locator. And just another note, we're not actually going to use the root control here during the training process. So that's only going to come into play on deployment when if we want this thing moving around the scene, we want to make sure we get the position of the IK handle with respect to that root position. And then if we just train with respect to root position at the origin, the math will all work out. So we're going to start. I'm going to, again, clean this up a bit. We have pivots, root, and then we want a random angle generator to start. Get as much room as possible here. So the way this is going to work is we're going to want a random value in a range. So I'm going to create a new compound called random value in range. And then inside of that, we want a random array, random value array. We want to pass the size and seed up. And then we're going to multiply. Those values are going to be between 0 and 1, but we want a range in our degrees here. So an axis might go from minus 180 to positive 180 degrees. So we want our random values to scale. So we want to subtract the max value in our range and the min value, and then multiply our numbers here that are between 0 and 1 by that, and then add that input with the minimum. And that'll produce random values in a range. So if we try this out, let's go from like minus 10 to 10. Let's call this 50, and then print that array. All right, you'll see 50 values between, 50 values between minus 10 and 10. All right, now we want one of these for each of our axes here. We're going to pass the size and seed up. The size, I'm going to rename this as numSamples to be clear. I'm going to paste this. Now for the seed, I'm actually going to disconnect these, and if we use the same seed for each of these, they're going to do exactly that. They're going to generate the initial values are all going to be the same. Those values between 0 and 1 are going to be the same for the same seed. So we want to use a different seed for each of them. So I'm just going to increment by 1, and then increment by 1 again. So each of these will have a different random seed, randomization seed. And then we want to pass out the minimum max for each axis. So I'll do this quickly and skip ahead just because this is a bit tedious. I'm just going to connect all these and then rename them. Okay, and then lastly, we'll just connect these to our output here. Rename. So now if we go up to our sample generator here, we have a node that will generate random angles for each axis. And then we want to pass the array of random angles into our FK solver and then get the resulting transforms. So to do that, we're going to use a for each once again, pass in our pivots and our root. In this case, we don't want these to be iteration targets. We want theta 1, 2, and 3 to be iteration targets. So now for each index in here, we're going to get our random value for each one of those, send it through the FK solver, get the output, and then stack those together. So if we go back to our main graph in the XZZ solver here, we basically want everything except the rig scope. The rig scope isn't going to work well inside that for loop. So I'm just going to copy this, paste it, head in here, delete the rig scope, and this should actually be good to go. And then cut and go into, once again, that for loop that's computing the samples, paste. Connect our pivots, our root, theta 1, theta 2, and theta 3. And then again, we're going to use our access transform matrices node here. So now it's time to think about how we actually want to construct what's called the feature vector. So we have an input feature vector and output feature vector. These are just going to be flat arrays of values, one for the input of the network and one for the output of the network during training. So in that initial slide, you'll recall that the idea here is to have our XYZ location as our input, and then we want to predict theta 1, theta 2, and theta 3. So here's what we'll set up the construction of those feature vectors, and we can play with how we do that in a little bit. So I'm going to pass out my transforms here, so we can use them later. We'll do a last in array. So what we're going to do is this is again the arrays for the world matrices for each joint, and we want the position of the last one, and that's going to be what we're going to learn on. That's going to correspond with where we want our IK handle, that target to be. So we'll do last in array matrix to SRT. That'll give us the translation. This will come in as a double. We'll make that a float. And then this is of type float3. So for a feature vector, we actually want to flatten everything out. So it's one array of floats. To do that, we want a vector3 to scalar. That'll break the components up, and then we're going to build array. So this will be an array of a flattened array of floats, basically. Take our outputs over here, and this is going to be our input features. Now for our output, again, we just want theta1, theta2, and theta3. So for our first pass, we're just going to naively pass these as is. Now, in machine learning, there are many different ways you can represent. Actually, in general, there are many different ways you can represent rotations. It turns out that networks like certain rotation representations better. And a lot of it depends on the task. So in some cases, you'll use quaternions. In some cases, you'll use the rotation matrix directly. In this case, we're trying to predict individual values as opposed to a series of values all related to a single rotation. So we have one value per rotation here that we're trying to predict. So the idea is we should be able to just pass those through as is. We can even keep them in degrees. And then we'll just do that as a first initial pass and see how it looks. So I'm going to connect this, and this will be output features here. And then the last thing I want to do is pass in that float3 value representation of that last point. And that's going to be for visualization purposes. We're going to be able to visualize every sample by its effectively an end position of the rig for that sample. So effector translation here. All right, so now we have our generator here that's computing samples. We're going to want to connect the number of samples and the seed out to the top level for control. And then back inside, we want to pass out our transforms once again in case we want to do any visualization on the actual kinematic rig. Input features, output features, and then we're going to make a diagnostic scope here that's going to be a point scope. So we're going to construct points using these end effector locations for each sample and do a point scope. All right, before this is going to work, the last thing we need to do is change our limits here. So these look like they kept those values from my test, -10 to 10. Let's just, we can go back up and actually take a look at how this rig is designed and what the actual rotation should be like. So if we look at theta1 here, try to crank this up. So this has a rotation, sorry, make this smaller here. So on one side, on the lower side, you know, we can handle some intersections, but we'll try to keep this like somewhat nice looking here. Say maybe 50 degrees on the upper bound, and then similarly, looks like it can handle a little bit more on the top here. All right, so maybe like -80 on the minimum, and then the upper. Let's do 50. All right, so similarly on axis 2, just for now, like this looks like it could just keep going and going and going. Typically for rotations, you don't want to pass like plus or minus 180 degrees. And then similarly for axis 3 here actually does have a hard stop. So let's try to find that. All right, and somewhere around there, maybe 160, and then on the other side, where it starts to collide. So -70, and then what did I say, 160? So we'll do 160, -70, and then for theta2, let's just for now do plus or minus 180. Okay, so now we've set up our limits for our data generator. And so if we turn on our point scope here, and then make sure we have some samples, okay, point scope, if we're getting points here, oh, there we go, change the scale, and that is 50 samples. And then we can really crank this up here, so we can make this whatever. I like to start with somewhere in the low tens of thousands just to start testing. So we'll just do 10,000 there. You can see this nice cloud. So that's basically the working range of this rig. And then once again, if we actually change our initial pivots, I'm gonna hide the rig itself. If we change our initial pivots, you'll see that the data that we're generating procedurally updates, which is super nice. So you can see that cloud change as the actual geometry of our rig changes. So it's a really powerful part of this workflow. Back into Bifrost. And then the last thing I want to do is I want to actually use our rig scope here to visualize a sample. So I'm going to make a new compound called sample scope. And we could set this up any number of ways if we want any different slice of the data. So I like looking at this cloud of end effector positions, but we could have some visualization on the actual input join angles and whatnot. So just for now, I'm going to set this up to similar to how we set up the initial rig. So let's drop that in. We want our geometry, we want our transforms, and then we're going to pass in first, actually before I pass in the transforms, this is going to be an array of transforms. So each element in the array is going to be the entire rig. Each array index is going to correspond to a sample. Each sample has its own essentially rig representation. So before I plug this in, I actually want to delete this. I'm going to pass it in this way. So pass in our array of array, pass in geometry while I'm here, and then I want to get from array a sample index of our choosing. So if I once again hide our training array here, we can hide our generator and then have a single scope sample. So as I iterate through here, this is picking an index out of our training data to show the rig state, which includes the end effector location. We can pass in our input and output features, and we could print those out per sample. For now, I'm not going to do anything with them, but I will just set them up just in case. Get from array, set up the index, copy paste that, change the port. So now get the input and output features and transform based on one input index for the sample we want to visualize. Okay, so now we've constructed our input features and output features. The next thing we need to do is get them out of Bifrost so that we can train on them using PyTorch. The way we're going to do that is to use the brand new write NumPy compound that was recently added by the wonderful Bifrost team. And we do this twice, one on the input features, one on the output features. So I'm going to copy paste this, start with our input features and output features. And then really the only thing we have to do here is set up our directory that we want to save to. So and select this little folder icon. I'm going to create a new folder on my desktop just to make it easy, and we'll use this folder for training as well, so we can save our train model weights in here. So I'll start with a new folder. I'll call this Bif DL tutorial. And then inside of that, just to keep everything organized, I'll create a data folder, and then we'll call this V1, and then we can save different iterations of our training data if we want to different folders. But for now, let's call this V1, and then this one will be called input features. And for now, make sure if you're going to follow the whole tutorial, stick with this naming convention because it matches the training script. So if you change what your features or what your file's called, then just make sure you change that on the training side too, so you're reading the right files. And then I can copy this onto my second node, paste that, and then remember just to change the input here to, or the name from input to output features. So if I go ahead on here, and these are both enabled, but if I pull up where the save location is, we'll see there's nothing there. So what Bifrost is doing is it's not computing things it doesn't have to compute, so we actually need to tell these things we want to compute. There's a number of ways to do this. The easiest for now is to actually just connect the success port here to the output. This is going to send it to Maya. That way Maya essentially pulls on the port and causes these to compute. So now if we go back here, we can see our output features has been successful, but not our input features here. And somehow we lost our file path. I must have cut that instead of copying. So let's redo that. Input features. All right, so now we see that the file path is correct, and we have our input and output features saved as arrays in .mpy files. In the next tutorial, I'll show you how to import these into PyTorch and then finally train our model.